Okay, so now we're going to talk about databases. Up to this point, we've been working with data, but the data that we've been working with is data that we're basically just storing in memory. So if you think about our Twitter JS, we're storing our tweets in memory. If you think about our weekend assignment, where we're storing our products in memory. And so really, when we end up doing this, we're sort of limited as to how our data ends up getting stored. So one thing to sort of think about, our next step is to move toward databases, is to think about what is a database. So if we think about things that end up holding information, we can think about a number of different things, whether it's a spreadsheet, yellow pages, a file cabinet, a tweet, right? Any number of things that you have here. But if we sort of think about the two things that are really important in terms of working with an application, you want your data to be persistent, meaning that you don't want to store it in memory. If someone took the time to end up creating a new product or to add a tweet, you don't want it to disappear if the process ends up going down, or what I should say, someone restarts the application. The other thing is that you want it to be accessible. So you want to be able to possibly get the tweets by a particular user, get the products by particular categories, or get a list of all the different products. So when we think about a database, there are two words that end up coming to mind. A database is going to persist information, and that data is going to be accessible, and we're going to be able to access it via code. Okay, I mean, we'll find out that within this workshop, we're going to be able to access it via code. We're also going to be able to access it via a command line. For all intents and purposes, it's pretty much the same thing. So our data is going to be organized, it's going to be queryable, and it's also going to be manageable. And those are three things that sort of separate out our databases from being able to store our data different ways. I mean, theoretically, we could take our data and store it in a text file. And if the data is simple enough, that could be totally fine. But as the data gets more complex, we're going to want to make sure that our data stays consistent, which is something that's very important. We'll find out that you could end up doing that by using tables and using relations and constraints and that sort of thing. So before there were these things called relational databases, how did things work? Well, I mean, in the end, what you had is you had different files you had different applications, and those applications were tasked with not only the processing, but also with storing the data as well. So each of the applications sort of kept their own data file, and an application had the ability to sort of query data. Here we can see a checking application, a savings application, various loan applications. And the application itself was responsible for both the data and the business logic. Now, sort of the advantages to this is that you didn't need any sort of middle layer, right? You had custom solutions for each of these applications. But the problem is that if you wanted to change the system, someone who's working on one application, they go to move to another application, they have to relearn how the data is stored in that particular application. And also, if there was reasons to sort of access data between applications, it became a lot more problematic to do. So what you ended up happening, instead of each application being responsible for its data, you had what was called the DBMS, which is a database management system. So that the different applications could have their own logic, but a database management system would sit above a shared database. And so you had one layer that had access to the data. Theoretically, this was also a way that non-technical people might be able to access the database from the database management system without even necessarily having to go through an application. They would be able to basically just query the database management system. But the bottom line was that you had this sort of middle layer that the applications were relying on to manage the data that they would be using. So sort of the father of relational databases was this gentleman by the name of E.F. Codd. And his whole thing was basically defining what was called the relational model. So this goes back a ways, and he defined this relational model. He ended up writing this alpha that was never ended up implementing it. IBM was slow to adopt what he did. There was actually a team that was formed without him, and they ended up coming up with this structured English query language. And this was basically copied by Larry Ellison, right, who went on to form Oracle. And it became a standard way of communicating with the database. So a standard way of getting the data that you wanted to out of the database and getting the data into the database. So here's a photo of an early photo of Oracle. Shows 4 probably pretty wealthy people. So why do we care so much about databases? Well, they're ubiquitous. They're all over the place. They're standardized. So, if you learn about databases and you move to a different stack, the database part of it is probably going to be the same, right? The way that we'll find out that the tables end up relating to each other. There's other things that are important too here. But the main thing is that the data itself, the schema, or how these things are designed, can be pretty powerful. And a lot of times this is done in a way that you want to be able to get at your data quickly, but you also don't want your data to be consistent. And this is something that we'll end up talking about. This is what foreign keys allow us to do, and this is why we don't put all of our data in one tremendous table. So when we think about relational database management systems, common thing is that we end up creating tables. So for instance, I'm going to show you an example where we have a users table, where we have a departments table, maybe we have a groups table, maybe we have a user groups table. And so the data itself is stored in tables. And what programmers can end up doing is they can use this standard query language to determine what the data is that they want, but it's the RDBMS that will determine under the covers how that data ends up coming back, what the execution path is of that data. And again, the RDBMS is supposed to look and see how the data is stored, what indexes there are, to determine the best path to get the data. The other thing about this is that this can be multi-threaded, where you could have multiple users end up accessing the database, as opposed to storing everything in a file, which could be problematic if multiple people are opening up the files. So when we end up thinking about definitions of a database, we're thinking about a collection of tables. Another word for that is going to be relations. Tables have columns. Another word for that is going to be attributes. And when we end up inserting a record in a column, that's going to be a row. Another word for that is going to be an instance or a tuple. Some rules that are there are that duplicate rows are not allowed. And one of the things that a lot of databases put constraints on is to say that a database table or a database relation is going to have a primary key that enforces the fact that 2 different rows are not going to be duplicated. So the difference between sort of the schema and the content. The schema is going to describe the blueprint for the data, right? Another way of saying that is the shape for the data. So, for instance, in a user table, we might have a field for the first name, which is going to be a string, a field for the last name, which is going to be a string, and maybe we have a date of birth, which is going to be a date field. So we could sort of define the shape of the data that's going to go into that table, as opposed to let's say we were just storing our data as a line in a text file. We could put whatever we wanted in here. Here, a schema is basically enforcing the integrity of our data. The content itself is going to be the data that's in a particular row. So, maybe a name is going to be Bart S. Maybe, 10 is going to be some department or something. Maybe M is going to be a gender. So SQL is going to be used to perform these CRUD operations, to create, to read, to update, and to delete. So we'll be using inserts to insert rows in a table. We'll be using select to select what data we're getting back from the database. We could use update to update existing rows or a particular row in a table, and delete to delete rows. There's also the ability to use create in order to create the tables themselves. So to create the relations, and also how the relations interact with each other. So let's take a look at a very simple couple of relations here. We've got students and we've got schools. Let's just look at those two on their own, right? So a student has an ID, a student has a name, a student has an age, and a student has a gender. A school is going to have an ID, a school is going to have a name, and a school is going to have a level. So if we wanted to have a scenario where we were keeping track of enrollments for students, we could have a third table where that table would have a student ID and a school ID. So we could see that Bart, is at Springfield Elementary, Lisa is at Springfield Elementary, Jim is at Brook Middle School, and Joan is at Springbrook High. So, just looking at this, we could sort of see that there's no enrollments in Simpson University. And that might be a query that you would be interested in finding. What schools have no enrollments? What schools have the most enrollment? And when we look at something like this, even though we're not showing it in this table, theoretically, I would assume that a student could have multiple enrollments. And if you were keeping track of enrollments, maybe there would be a third column in the enrollment table, which might be something like, school year or that sort of thing. But that would be perfectly legitimate where, a student could have multiple enrollments. And we could see here right off the bat, a school for sure has multiple enrollments, or else you'd only have, one person in the school. So when we end up looking at, the first thing we should look at is how we end up going to select data. So if we do a select star from the student table, and just as an aside, it's a little bit more common, I think, for the tables to have plural names than it is for them to have for them to be singular. So in the real world, I think you'd run into this more as a student's table. But one of the things you could do is you could query that student's table, and this is basically going to get every column from the student's table, but there's a restriction on it. There's a where clause on it. And the where is, hey, look, we're only interested in those students with an age that's greater than 12, right? So this would only get students Jim and Joan. So, little SQL joke, it's cute. Let's look at something that's a little bit more interesting, right? Let's say that you wanted to find all the students from Springfield Elementary. So the student table on its own doesn't list the school. And, there's a reason for that. The reason for that is that a student can have multiple schools in the form of enrollments, and those are stored in the enrollment table. So how do we go about, joining these things to find all the students from Springfield Elementary? Now, again, we could look at this and we can sort of think about, all right, Springfield Elementary has an ID of 1. We can see the school ID, and we can see that Bart and Lisa have enrollments in this school. So, this sort of describes what we're doing to go ahead and visualize it. And so, what we're basically able to do is to do a join and to say, hey, look, when we end up looking at this enrollment table, right, this enrollment has a common field with the school based on the school ID, and the enrollment has a common field with the student based on the student ID. So how does that look in terms of, running that query? So what we can end up doing is that we could look at the student table and we could join it on the enrollment. And we could say, hey, look, the ID of the enrollment is going to be equal to the enrollment's student ID. But then we could also do another join, and we could say, hey, look, this is also going to join on the school, where the enrollment's school ID is equal to the actual school's ID. And this is a very common way to join, and this join would be called a many-to-many. And sort of when you think about a many-to-many, a student can have multiple enrollments, and a school can have multiple enrollments. So if we wanted to get this, if we're only interested in Springfield Elementary School, we can basically limit our results by saying, hey, look, we're interested in these relations, but we're only interested when the enrollment school ID is 1. On the same token, if you were joining on the school, you could also, if you didn't know that the ID is 1, you could say where, school.schoolname is equal to Springfield Elementary. And you'd end up getting, basically that same result set. So let's talk a little bit about joins when we have two tables and how we end up doing these joins. Sometimes we're going to want to do an inner join. Sometimes we're going to want to do a left join. Sometimes we're going to do a right join. And there might be circumstances where we want to do a full outer join. So let's look at some of these. It's, I think, a little bit easier to see with some examples here. So let's say we had these two different tables. We had pets and we had owners. And the one thing to sort of think about here is that if we have owners and we have pets, and each pet, has a particular owner, what we're going to end up getting here is we're going to only end up getting the owners that actually have pets, right? So we could look at the pets table. We could see that, we've got an owner ID of 4, 1, and 2. The only owners that we're going to come up with are going to be the owners that have the IDs 4, 1, and 2, and that's exactly what we end up getting, right? So 4, 1, and 2 are the ones that we have, and then we end up getting their pets' names as well. So basically, it's when we end up doing an inner join, and this is very common to do, it's limiting the data that we're going to be getting. I mean, we're always going to be limiting the data with the except of the full outer joins. Let's look at one other one here. So now let's look at a left join. So we've got our owners and we've got our pets. And what we're saying here is that, hey, look, we have our owners. And another, the syntax I usually use for left join, I guess it depends on the syntax. I usually use left outer join. And what this says is, hey, look, even if an owner doesn't end up having a pet, so we can see we've got owners, 4, 1, and 2 that have pets. This owner called data doesn't have a pet, but we still want to include him in the results. The left outer join would end up doing that, right? The owner does not have a pet, but we want to include him in the result, and that's one of the reasons why we see that the name of the pet is null, is because that owner doesn't have a pet. But if we ended up just doing a join, we wouldn't end up getting that result. So this is the record that we wouldn't have before that we end up getting now. Very, very similar for the right join, where in this case, we could have pets that don't necessarily have owners, but we still want to include them in the result set. And in this case, we've got Carol the lizard, who we want to include in the results set, and we end up getting her from this right join. And again, I think I would end up running this with a right outer join. And I guess if you want to get the records for both of these, you would end up doing a full outer join, which is not, at least in my experience, all that common, where you would end up getting all of the owners and all of the pets, right? But some of the pets don't have owners, and some of the owners don't have pets. So we see that Carol doesn't have an owner, and Data doesn't have a pet. So that gives you an idea of the different types of joins that you could run. before we go into the workshop, what I want to do is do a couple of examples with a simple database so we can see how these joins work. So before we go into the workshop, let's see how we could go about querying some data. I've got a very simple database set up, and we could actually investigate it. What I'm going to do is I'm going to say SQLite 3, and this is going to be my Acme DB database. So one thing you could do here, if you wanted to see the tables, you could say tables here. You can actually look and see, what the blueprint is for these tables by saying schema users. So a user has an ID, a name, and a department ID. We could say schema departments. And here we could say department has a primary key and a name. We could say schema groups. And a group is going to have a name. We could actually select some data too. And just to round this out, we could say schema user groups. And just to sort of, let you in on this, the user groups is a many-to-many relationship where each record in the user groups has both a group ID and a user ID. So when we sort of think about the cardinality of these relationships, and we look at the users table, a user can have a single department. And of course, you could have multiple users that have that same department, so a department can have multiple users. A user has one department, a department has multiple users, and that's what we end up calling the cardinality of this relationship. So for instance, if we wanted to do, select name from users, we're going to get all of our users here. And here, if we end up saying, I want to select, I want to do a join and maybe find out, let's say that I wanted to say select name, and I could also do department ID from users. That's a department ID. Shep actually has a non-existent department, which doesn't really make a lot of sense. In fact, let's actually get rid of Shep. One of the things we could do is we could say delete from users, where, and I actually know his ID is 4. And Shep should be gone, and he is. So here, a little bit simpler. We've got these 3 users, but we see that Curly doesn't have a department ID. So if we wanted to get the user with their respective department ID, the way that I always like to think about it is, what data do I need? Well, I need the name from the users. From the departments, I also need the name. I surely need the users table. And I'm going to join that users table on departments, join departments on departments.id equals users department ID. And so that'll give me 2 users, okay? But what you saw before is that we've got one user that's left out because they don't have a department. If we wanted to get that user, we could specify join actually is the same as an inner join, synonymous, give us that same result. But I could actually do not an inner join, but I could do a left join. And that'll end up giving me Curly as well. So if you get a left join, you're basically saying, hey, look, I want all the users, even if they don't have a department. Of course, you could always go and say, hey, look, I'm only interested in the users in IT, where departments.name is equal to IT, and you'll end up getting that. And in this case, it really doesn't make a lot of sense to have this left join, because I'm actually going to be filtering my results on a specific department, right? So this would give me the IT users. On the same token, if you wanted to basically just get the users that did not have departments, another way you could do that, let me clear this out, is you could go over here, let's get rid of that. Let me get out of this for a second. Let me go back in. Sorry about that. So this is going to be here. Let's say we wanted to get all the users that had no department. we could say select from users. You might think you could be able to say department ID equals null. Doesn't really work. It actually gives us a syntax error. And actually, it's giving us syntax error probably for another reason, so let's make sure we got it for the right reason. Select name from users where department ID is null. That doesn't give us what we want. When we're dealing with nulls, we actually have to use the SQL is null. And now we end up getting curly. And if we wanted users that had departments, but we weren't concerned about what department it was, we could say is not null. Okay? So we can see how we can query this relationship. And this is sort of a simple cardinality that says that a user has one and a department has many. Now, sometimes you have relationships that are a little bit more complex. So let's say we're looking at our select name from groups. So let's say that these were sort of groups that employees would end up forming, and an employee could end up being in many groups, and a group could have many employees. So these are the two groups that we have at Acme, and if we select star from user groups, we could see that we've got user one, which is Mo, has a group ID, and this is going to be books. Larry's is also in that same group, which is books. And we could see that Curly is the only person in the running group. So how could we go about querying that? Well, this is very, very much like our enrollment table. So let's say that we wanted to get the name of the users, and we wanted to get all the users together with all their groups. And granted, when we end up getting our results, we could get multiple users and multiple groups. That's what we actually expect. So what do we want to get? Always think about what you want to end up getting in your query first. That's going to lead you down the right path. So we can say, hey, look, we want the users.name, and we also want the groups.name. And where do we want to get it from? Well, we know we need to join the user groups. And when we're joining the user groups, we're going to join it on, and here we can actually even set this up, right? We know we're going to get from users, right? We're going to join the user groups, because we can't go directly from user to group. So we've got the users, we're joining the user groups, and this is going to be on the user's ID is equal to the user groups dot user ID, because that's how it's stored in the user groups table. And then on top of that, we're going to do another join, and we're going to end up doing it on groups. This is a very common thing where you have this many-to-many table. So users is related to user groups, and groups is related to user groups. So now we join on groups, and we say where the groups ID is equal to the user groups, and in this case, it's going to be the group ID. And that should end up giving us, hey, look, Mo is in books, Larry is in books, Curly is in running. And if we wanted to filter this, we could always filter it. If we only were interested in the people that were in running, we could do a filter and say where groups.name is equal to running. And that would in fact be Curly, right? But if we ended up saying books, that would end up being Mo and Larry. So for all intents and purposes, and again, these levels can end up going pretty deep, but the relationships that you're usually interested in modeling in the end are going to be a one-to-many, which I think works for a user and a department, or we could have a department can end up having many users, which makes sense, right? Because the department ID is stored in the users table, and many users could have the same department ID, or we could have that many-to-many relationship, which works with things like enrollments, which ends up working pretty well, where a user can belong to multiple groups, and a group can end up having multiple users. So that kind of wraps up the SQL lecture and probably gives you enough information to go in and get started with the workshop.